Well, welcome. Last session of the day. Been a long day. I know that I've learned a whole lot. I hope that you haven't learned everything you could possibly learn and you'll still pick up one or two interesting things from this talk. So how many of you were possibly not at my keynote this morning, or were you all there? One? Okay, two. Well, I'm sorry for that. I'm going to do a quick sort of rerun through about 3 slides of the sort of the business case around it, and then I'll go right into the technical details. So I invite you in a couple weeks. I'm sure the video will be on the site for you to look at the keynote as well. So I'm from Comcast. Specifically, I work for Comcast Cable. We provide home internet, phone, video, home security, and there are 30 million customer relationships at the end of 2018. And this use case is specifically for high-speed internet. We have 25 million residential internet subscribers, and we added about 1 million in the last year. And our goal, I work for the Customer Experience Technologies organization. Our goal is to provide the ultimate in customer experience. As I mentioned this morning, the use case is to basically try to figure out from customer experience indicators whether the customer is having a good experience or a bad experience. If they're having a bad experience, if they engage with us digitally, can they self-service a solution and basically restore their service within a few minutes? And if they can't, if they have to talk to an agent or if a technician has to visit, can we provide predictions, diagnoses, and recommended treatments to help solve things faster and cheaper? So from a high-level perspective, all of the systems that are responsible for delivering high-speed internet service are sending these customer experience indicators to our platform. The platform is then running models to produce diagnoses, recommended treatments, and making them available in a data store for the customer engagement platform to then get those right away. This morning I presented an interactive demo of someone on a My Account app, basically me playing the role of trying to restore internet for my son. Ironically, my son texted me at 3 in the afternoon today saying that Wi-Fi was out, but it was due to a power outage. It had nothing to do with the service. So there are a lot of systems that provide the service, and we've engineered it so that each of these systems are sending us basically red or green indicators for each customer account continuously. And when we started this project about a year ago, we had a little trickle, and over the past year, we've ramped up to the 5 billion. So in this very quick example, and this is I think the last repeat slide from the morning. In this example, perhaps it's green from the central areas to about the node fibers that are branching out, and it's red from the neighborhood on down. There's nothing that a customer could do to restore this in this particular scenario, but we know from an overall picture of this customer's experience that most likely there's already a truck out there trying to fix it, but they're not having a great experience overall. Right, so this morning I talked mostly about the business case. I'm going to go in moderate depth on sort of an array of problems and challenges that we had in scaling the system over the past year. Some of them are more architectural principles surrounding Flink. Some of them are with Flink themselves, but basically if you're starting a new solution or growing, you'll probably hit different aspects of this throughout the experience. And as I've learned from some of the talks today, many other people have faced the same challenges and have very similar resolutions. Right, so last year my colleague and I presented our machine learning operationalization framework, and that is the basis for this use case. And I'm not going to go into great detail on this, but just wanted to show you the starting point where we were a year ago with taking this framework and then starting to put this real-time use case on top of it. And in a very, very high-level sense, a requesting application can say, I want to execute a machine learning model to make a prediction. It's going out and getting features or pieces of data in order to make that prediction. It might have to get them from externally. It executes a model, and then it stores the prediction. And everything that's in sort of the darker blue, hopefully comes out, is kind of a REST service, and everything that's in the lighter blue with the squirrel logo is Flink. And I'll show you the slide again in a few minutes. So the first problem was a very simple one. We had 4 of these customer indicators coming in starting about May of last year, the very first 4 to go online, and it was about 175 million a day. That's still a lot of ML models to execute to get predictions. Do we want to execute every single one of those? Well, we decided that that's a little bit too much. So putting a very simple trigger in place So we said, we have these different indicators for a customer. They're mostly green. Over time, some come in. But we can detect, using Flink state, that a particular one turned to red. And that change in state is enough to say, now I want to run a new diagnosis to overwrite whatever was there previously. So we were able to take the 175 million data points, putting Flink state in the middle and checking as each one came in, whether it was a change in state or the same thing that came in previously, and turned 175 million data points into just a few million. That was manageable, and that worked very nicely. So the second problem we hit was the rest problem. So as I'm sure you've experienced, when you're architecting a system, you can have asynchronous, you can have synchronous, and everyone likes to have microservice architectures, or maybe there's an existing service out there that you need to reuse from within your Flink architecture. So our original architecture was designed to be independent and have REST endpoints for everything from calling the execution pipeline in the first place to going out to a pluggable model to execute. Well, when we put our streaming use case in front of that, and we had a nice separation of concerns here. We had the data streaming part, and then we had the model execution part. We quickly ran into the problem that the ML framework, while it was REST, it was isolated by design, but in Flink, scaling async I/O in order to call REST services is kind of difficult. It's not as elastic as using, say, Kafka, right? So there are a few approaches that we took to solve this problem. The first thing we did was, let's try tuning async I/O. With simple math, you can figure out how many transactions per second you can hit. It's really simple. Number of slots, number of threads per slot, what's your latency for a particular HTTP REST call, divide it out. So if you have 12 slots, 20 threads, and let's say a 300 millisecond service, you can get 800 per second. And the couple of parameters you can change in Flink to accomplish this. If you're using, for example, an Apache HTTP client, there's a couple of parameters, set max total, max per route, and let's say you want to say, I want to do 200 rather than the default 100. Similarly, in Flink, you want to match that. In Flink, in the async I/O, there's a max outstanding capacity parameter, and if you're going to have 200 in your pool for the HTTP call, you want to make sure the max outstanding in the Flink async I/O is similar. The other thing that we had to do was throttle our rate of call. These services sometimes can be overloaded, especially if you have peaks and valleys in your load, and all of a sudden you're calling at a huge rate, and the existing service may not scale. So we put a rate throttle in there as well. But that only bought us a little bit. So what we really wanted to do is re-architect and take out our REST calls entirely. So the two X's are where we took a REST call to get into the ML part and just use a Kafka queue in between the two. And similarly, we moved the model execution from a separate service and put it in line with Flink, which was possible to do because we were using a Java-based model for that particular execution. If you had a different REST service that was wrapping Python or something else, that might be a little bit more difficult to do. And then we iterated once more and decided to get rid of the other two REST services, the ones that were storing things in the feature store and also the output sync. Now the feature store was interesting because here we were using a typical database to store our features, our data points that were coming in. So we transitioned that, and I think I mentioned that later in the talk as well, to using Flink local state or queryable state in order to store all those features. Right, so now we have a nicely Kafka-esque architecture without REST. Right, so the next thing, so as you know, when you're scaling systems, you have four main concerns. You have RAM, CPU, I/O, and disk speed, and those are kind of your constraints that you get to play with. There's probably others, but those are kind of the four main ones. So has this ever happened to you? You find a nice utility. And in our case, we've been using Jolt, which is a JSON transformation library, and we had a little utility class. So we create a new one of these, but we don't cache it. Inside it, it does an object mapper, but that isn't cached. Parses the JSON into a map internally. It loads and parses some transformation spec, which is also JSON, but that isn't cached either, even though it's reused billions of times. Serialize it back into a string. Oh, but now we're going to take the string and make another JSON out of it, read into the path to get a particular value that we need, and in this particular code, which is real code from our 1 year ago, catch an exception if we don't find that particular path. So we have created 5, 6 objects, transform JSON into string, into map back to JSON. It is not efficient. So we made that a little bit more efficient. And in any kind of refactoring, I suggest that you go and look at your code and see what you can do to make it more efficient. Create your object mapper and cache it, because if it's thread safe, you can reuse it as much as you want. Parse it once, and we made a lightweight utility to traverse it and get the value we need and not throw exceptions if it's not found. And why does this matter? That matters because the more objects you create, the more garbage collection and the more CPU you're using for really unnecessary functions. And CPU is probably the most expensive of those 4 things that you have to play with. There are also other ways within Flink to set parameters to get more object efficiencies. I will caution you that you have to either know what you're doing or read the documentation very carefully, and when you fail, be able to react. Because these are things that may have side effects if your code is not expecting objects to be reused. The first one, which is just saying enable object reuse, will reuse the objects that are serialized between operators, and also basically reuse it and unmarshal something into it to use it again. The second ones are semantic annotations, where for a particular operator, you can mark which fields you know are either absolutely not going to go into the output unchanged, or do the converse and say these particular fields that are coming in your tuple are going to stay exactly as they are and not be changed in your output. If you know that, then Flink internally can make a few optimizations and not do some operations. I have not looked at the source code of Flink to see what it actually is doing for that optimization, but this is documented pretty well on the Flink site. Right. So the next thing was the feature store problem. Now, what is a feature? What is a feature store? Data scientists like to call data features. So really, it's just data in a database. For our particular problem, we actually had 5 or 6 things we needed to do with this data. We needed to use it for our predictions. We wanted to save it for historical reasons to be able to train and retrain ML models. We also needed to put it into an overriding sort of current state store, or the online feature store, so that external consumers and UIs and such could pull the latest values of these data points at any point in time. And in order to do all this with the Flink flow that was creating these data points and features, we basically said, okay, we're starting off small. Let's just use an RDBMS. It's simple, spin it up in Amazon. And my quote is, hey, it should get us up to about 10,000 a second. We got 6 months on this, right? The problem is that since we were overwriting data, we were saying if the feature isn't there, put it there. If it is there, we need to update the value. That caused performance problems. And we didn't really get much beyond 3,000 per second with, I guess, the price we were willing to pay for a certain size of Aurora. And our input rate was growing so rapidly that soon we were at 20,000 a second, and this didn't work. So we did a mitigation where we said, you know what, we're not going to store every single data point that comes in. We're only going to store the data points that are associated with one of those diagnoses triggers. The good news is the volume was much, much less. The bad news is it was worthless. We only had a few percentage of the data points. They could be outdated. It could be that some of the data, which is updated perhaps every 30 minutes, the value was from a diagnosis 4 hours earlier when there was a state change. So we really didn't gain much from this other than the solution kept on working, but we needed to solve this. One more thing that we did was, and I mentioned this earlier, we changed the write path so that we had a feature manager, which was for the prediction, separate from the feature sync flow that wrote that continually updated flow. So by separating out one Flink writer into 2 separate components, the one that we really didn't care about if it backed up a little bit, which was the online feature store, that could back up fine because we were writing with Kafka, and that was separate from the actual prediction flow, which really needed to be done as soon as a value came in. We've been looking at alternate data stores. After MySQL and Aurora didn't work, after we cut it down, we said we really need a solution to be able to write this increasing volume. We looked at Redis, Flink Queryable States, Cassandra, and briefly at some time series DB like Druid and Influx. We did some POC on Redis, and we realized since we only needed most recent data, we figured we could overwrite it very quickly, and it's in memory, it should be very fast. Somehow, between the size of the Redis cluster, and because it's in memory, it gets expensive quickly as well, we didn't get past 8,000 per second with our POC here. The Flink sync connector is in the Bahir project as opposed to in the Flink core project. It's not really cluster enabled. There's a couple of Java-based libraries that work with Redis. One's called Jedis, one's called Lettuce, and they have different mechanics for doing writing as sort of a batch or pipelining. We also wanted to use a clustered Redis for better failover, and none of these drivers really supported it very, very well because of the way that Redis is sharding. So we tried the POC. We said, this is okay, but it's not really working for us. So Flink Queryable State. First of all, it's built into Flink, and we were already using the feature for our feature store. When we had sort of a feature request and a feature response, you saw from those diagrams with the little pink thing, it was actually going and retrieving the data and bringing it back. It's scalable, it's fast, it's Flink, we know it. And our use case, our read load was actually very, very low. The write was intense, every single data point that comes in, but the read was only for some interactive use cases and UI presentation. The problems is it's expensive because you are deploying and managing Flink clusters. It's not easy to use as a managed service, like something we can spin up on Amazon. It's not really touted as a production capability, although it's maturing over time, and it's also not really a database technology. It's a KV store. It does have RocksDB under the hood, but it's not really Cassandra or something that you can say, this is a database, it's meant to be a database, it has all the operational characteristics of a database, and I know how to manage that. But we did it anyway. We said, for the moment, we're going to use it while we pursue the other options. So we created the bottom path, which is our model execution path, and that has the Flink local state with all those data points coming in. We also have a separate path, which is our online data store using queryable state, so that can be, once again, separately written to and queried by the requesting applications independent of the execution path. And actually, that is what we're using today, and it's still working fine as we try to discover whether we want to use Cassandra or some of those other technologies. Right, so the volume problem. This is all about the volume. We started in May with our first prototypes. We went live in production in the middle of July, and we ramped up the percentage of our customers over a period of maybe 2 weeks or so, and very soon we're at 100% of our customers. We added new data point types, so we started with about 200 million, and by September we were at 600 million. And all these indicators, so all the systems that are sending these health indicators of the customer, you want to get that as up to date as possible. It doesn't really help you if you knew that the customer was in great standing 16 hours ago when the customer's calling up now and saying there's a problem. So we started with some of these data points once every 24 hours. And then we ramped up many of them to once every 4 hours. So you can imagine the volume's increasing. And some of these data producers really want to do it every 5 minutes. So what happened? Our Kafka latency started increasing. We noticed that the Flink cluster could not keep up with the rate of data that was coming in. Now, how do you optimize your Kafka and Flink interactions? So if you're familiar with Kafka, every stream can have a certain number of partitions, and every partition is read by one and only one thread. You can have multiple partitions going to a thread, but one partition will never go to multiple threads. So if you have 50 or 100 Kafka partitions, you want to either match that or have an even multiple so that you can spread the load amongst your Flink cluster. We actually scaled out our inbound data stream here, and I think we're currently at about 140 partitions or so. But that increased over time as the volume increased. On the right side, you can also adjust the Kafka configuration. The numbers are not important. What's important is that by making the batch gets chunkier, you trade off latency for throughput. So you can get more at a time, and you increase your latency by whatever it's tolerable. So we increased, for example, from a few milliseconds to 50 milliseconds to wait for to fill a batch and send it off to Flink. And then and there are different parameters for both producing and consuming that have similar effects. Right? Another problem, you may have heard about back pressure throughout the day, and if you've worked with Flink, you know that back pressure is one of the most evil enemies that you'll have to encounter. So we had a couple of operators where we were doing, here are two examples. We had a async IO, which had a 60-second timeout, and we had another sort of Kafka-based request response with a stream join, which had a 5-minute window to kind of wait for the responses to then send it down the line. If the second one started backing up because the REST service was slow, that would impact the previous one, and things would time out of there, and the back pressure would just cause the solution to just not work. Another problem or symptom that we observed is the network I/O. And here's kind of a base primer to what's happening with a Flink cluster in I/O. So when you're reading from Kafka, each partition is going to a thread, but there actually is not a good way of determining which thread is going to each node. So it's kind of random. So if I have 3 nodes, all those data with whatever keys are in there are going to a particular thread Flink consumer. And then if I do any kind of key by shuffle operation, it's going to want to send the right keys to exactly the same thread from any of those Kafka consumers. So you have kind of a crosstalk in the middle. And then finally, at the end, if you're doing a write to Kafka again, it's going to go out of your network. So between the inbound, the crosstalk, every time you do a key by, and then the outbound, it's very network intensive, and depending on what your I/O is, what your throughput is, and how big your nodes are, it can just start to clog up. We actually found, and you can forgive the math because I started to try to figure out how many of our messages were causing how much of a 1 gigabyte I/O provision, but then I couldn't find out in Amazon what our actual provisioning was. But in any case, we found that we solved this problem by taking larger nodes but fewer of them. To reduce the amount of crosstalk, we found that going from, say, 40 nodes to 20 nodes actually improved our performance quite a bit, even with comparable CPU and VMs. I'm sorry, not VMs, cores, rather. Oh, and there's a very good read on the Viverica site. It's a blog that says how to size your cluster, and it has a good amount of detail about this particular problem. Right, customer state problem. So I talked about this morning how we are actually storing 2 kinds of state. And one state is the red and green triggers, which is basically each of these indicators is for each customer account number, whether it's green or red. And that's actually a very small amount of state. It's about 33 bytes per account. All in total for 25 million customers was about a gigabyte. Not a big deal. However, all those data points that had tons of supplementary radio signals and other measurements associated with it could be as much as 15 KB in JSON per data point. You take anything like that, and you multiply it by 25 million, it turns into a big number. For our 10 or so data points or types of data points that we collect, that really is about a terabyte of state. And that leads into the checkpoint problem. So when you have a large amount of state, it takes a long time to write that to disk. When we started out, it was taking about 2.5 minutes of writing a checkpoint, and we had it set to every 10 minutes. That was a lot of time when you're just not using your machine properly. We turned off the checkpointing for a while. We decided that since this was state that was being continuously fed by all these upstream systems, that if the system went down, it would only take a few hours to restore it anyway. So that really wasn't a big deal. However, once we turned on incremental checkpointing, that helped quite a bit. And we are unfortunately getting the problem of long alignment times on high parallelism, which is when you have different nodes that are processing at slightly different speeds, but they all need to align before you can take a checkpoint. And one last thing that we did to help with this is we have a couple of the Flink models, or ML models, that actually use 4 and 24-hour windows for state keeping. And instead of storing raw JSON for that, one of our engineers took basically a key value approach to those keys and values in JSON and mapped them to integer IDs, and it compressed it by about 90%. JSON is not exactly the most efficient way of storing data. Avro is much more compact, and protobuf and other things, but at least for the time being, we're receiving JSON. Right, so the HA, or high availability problem. I don't know how many of the 9 this is. This might be 6 or 7. We're getting through. I know that the Flink Fest is waiting for us on the other side. So we use Amazon EMR because it was very easy to provision. It's elastic, and we like managed services, so we don't have to operate everything ourselves. However, it is based on Yarn, and there are a couple problems with its high availability. One is that the master node is a single node. It doesn't use the Flink notion of where you can have multiple masters with failover. So if the master node goes down in Amazon's EMR, your application will still continue to run, but you can't manage it. It just becomes something that is sort of a zombie thing. So at some point, you have to kill it and restart it. The other thing that is not to our liking is we want to have multiple availability zone, which is kind of a different data center concept in Amazon. And every single cluster is going to be in one and only one availability zone. So you have to externally monitor that, and if a cluster goes down, you would either have to have a hot standby or create one from scratch on a different region to start it back up again. From what I understand, when you're running certain Kubernetes managers, you don't have to do that quite as actively, that it'll take care of it. We haven't explored that part too much. However, the good thing is that since we were writing our save points and checkpoints to S3, which is durable across availability zones, if one region goes down and you restart it from the save point on a different availability zone, that is not a problem. But we did have some other problems with EMR. Our sessions just kept dying, and we really couldn't figure it out for a while. And at some point, we figured that the temp dir is periodically cleared by Amazon, I guess to keep machines running longer, but that's where the blob store is stored by Flink. The good news is that you can configure that to not be in /temp. So there's two parameters, job manager, web tempter, blob storage directory. If you set those to somewhere else on the disk, that fixes that problem. And the other thing is, I don't know how many of you follow the Flink releases religiously, but there's often a point release that fixes a particular bug that was hitting you, and you're like, I really want to go to that next point release. Unfortunately, EMR, which to be fair, they want to make sure that things are stable and working before they release them to a customer base, but it can still be 1 to 2 months from a Flink point release until you see it in an EMR version. Sometimes it's frustrating, sometimes that's good, especially if you have a regression. 1.1 doesn't work, but 0.2 fixes the regression. But in any case, I'd love to be able to be on something besides EMR where I can say, oh, this next point release that came out, I'm just going to spin it up in our cluster, and we're on the latest version. So we're exploring that. I'm sure you've heard today of lots of people using Flink on Kubernetes. We have that in our sites, and hopefully we'll do that pretty soon. We were looking at Amazon's EKS, the Elastic Kubernetes Service, self-managing on EC2, or looking at the Ververica platform as well. And we think that based on our cluster sizes, we'll also get a little bit of efficiency from not having to stand up so many master nodes that are kind of wasted when we really just need sort of more elastic workers and tasks. Right. So the last problem was the really, really high volume and feature store problem number 2. So as you may have seen this morning, we started last July with about 175, 200 million data points per day. By October, we had hit 1 billion data points per day. 1 month later, we were at 2 billion. And then we turned on not 1, but 2 different experience indicators that added 3 billion per day each. These were the gateway modems, which have sort of health pings and health checks as often, depending on the model, as every 90 seconds. Most of them are 5 to 10 minutes. But that is a lot of data. So our application broke. It just, what was working with 1 or 2 billion did not work with another 3 to 6 billion. So we needed to do some vertical, some people have been calling things vertical and horizontal scaling for different things. I call horizontal scaling when you have the same application, you just add more nodes to it. And vertical scaling when you take different pieces of functionality and break them up either before or after the other functionality. So we did vertical scaling. We took these high volume data indicators and moved their functionality out to their own clusters, and we shifted things around a little bit. So the first thing we did was take that trigger, the red-green detector, and take those 2 high-volume data points and create their own trigger Flink clusters. So we took 3 billion data points in. We were sending only 50 million out, approximately, per day, into the model execution pipeline. And so between those 2 and the remaining data points, it was a manageable problem to have, and the model execution pipeline still worked just fine. The second thing we had to do is take our online feature store. So as I mentioned, we had now a total of about 1 terabyte of state. That wasn't working too well when it was all in one cluster. So we took, once again, those 2 high-volume data producers and set up their own queryable state. And then to accomplish that, from the requesting application side, they're saying, I want all the data points for a particular customer account, it would then know which types of features to get from which cluster, and it would assemble them and return that. So now we have a federated feature store, which is nice because we can expand that with all sorts of other features, other kinds of databases, and the assembly can still do its job really nicely. And then the third and fourth thing that we did is we took two of the other paths. One is storing our historical data in S3, and the second one is storing the feature store in the local state for the REST application. And then the third path is the trigger that goes into the model execution. We made that first Flink application up front perform all three and send it down 3 different pipes. And that worked pretty well because we already had the data in there. We already knew that we could send it on 3 outbound Kafka queues, and that way we're able to split the responsibilities. And even if the S3 feature sync backed up, it didn't really affect us too much. So this is a little bit complicated picture of our current architecture, but really what it is, it's the original architecture after we had taken out all of the REST and replaced them with Kafka queues, after we had taken out all the weird databases and replaced them with Flink local state. And then we have 3 paths. We have the historical data that goes to S3. We have the online feature store, which goes for interactive use cases, currently in queryable state. And then we have the model execution path, which goes to the store that then is accessed when someone calls up or uses their My Account app to try to get a self-service solution. So our current volume, I showed this earlier today. Most of our indicators all put together are about 725 million data points a day. Our 2 high volume indicators total 6 billion per day, so we're at a total of 7 billion data points per day. The size of the Flink clusters, if you add up all those different ones on the current architecture slide, we have 14 clusters, a total of about 150 VMs, 1,100 CPU, and a grand total of almost 6 terabytes of RAM. And what are we doing in the future? So this solution that we've done so far is for high-speed internet customers, which is one of our important products. However, we have a lot of other products like home security, voice, video, and business services, and we would like to expand the solution to those other product lines. Part of our domain is doing these predictions with ML models, and so we would like to take a more continuous approach to having the results of our self-service go back for historical model retraining. And lastly, as I mentioned earlier, we took the model execution and put it in with the Flink flow itself, but a lot of the data scientists want to do all sorts of interesting models which aren't necessarily conducive to being in that environment. So we are experimenting with Kubeflow and using gRPC to hopefully have a more effective non-REST but still interprocess communication to have that efficiency. Right, so with that, I'd just like to close and say we are hiring. We're solving some very interesting problems. We are based in Philadelphia in the new 60-story Comcast Technology Center, but we have offices in DC, Mountain View, Sunnyvale, and Denver. And we are sponsoring the Flink Fest that it will start in about 25 minutes. And so come talk to me or any of my colleagues who are wearing Comcast gray t-shirts. And thank you, and I'll take any questions. I'll take any easy questions. It's late. No.
So the stuff that the ML group wants to do as far as like additional cool stuff, I assume it's mostly Python-based. Okay, yeah, that's louder. So I assume they're doing Python stuff, right? The machine learning group, what they want to do. So how come, like, you didn't mention maybe trying to use Beam instead of, alternative approaches to being able to call out to Python stuff?
Right, so I would say that I don't know a huge amount of Beam in the last year or so, but when I looked at it earlier on, it seemed like it was a very nice API that abstracted being able to run on Google and Spark and Flink, but by taking those abstractions, you didn't have any of the fine-grained control that some of the more advanced features in Flink gave you, for example. So it's possible that may have changed, but I still feel like going to sort of a common denominator doesn't suit us very well. I did not attend any of the Beam talks today, but that's my impression.
Any more questions? No? All right. There will be a closing. Let's first of all thank Dave for the good talk.
Thank you.